Hello. Today I'm going to talk about my recent work that's going to be presented at SIGCOMM' 2024, titled CCAnalyzer, an efficient and nearly passive congestion control classifier. So let's first talk about the importance of congestion control algorithms and why we need a congestion control classifier. So imagine, as I often do, that you're Michelle Obama, you want to watch Netflix at home, so you connect to your home network and connect to the internet to watch. And let's say in the other room, your husband Barack has decided he also wants to watch some videos on YouTube, so he also connects. And let's say their access to the internet is only 30 megabits per second here. But let's also say that these two services want to send at much higher speeds than the capacity of this network. So ultimately, it's the job of congestion control algorithms, which I'll shorten as CCAs in this talk, to ensure internet services like YouTube and Netflix can share this overloaded network. Historically, CCAs couldn't share both fairness and efficiency. One of the first widely deployed CCAs, TCP Reno, had nice guarantees that in this example, each user could get half the link capacity as long as both senders used the same algorithm. Notably, they could do this without any explicit coordination between the senders. However, researchers and internet content providers have proposed a suite of replacements for TCP Reno to keep up with the demands of a faster internet, more diverse applications, and mobile users. Further, we've seen large content providers discuss deploying these new CCAs, including Google, Facebook, Spotify, Akamai, and Dropbox. So when we're moving away from everyone deploying the same CCA, we no longer have these guarantees about fair sharing. And so if there's more heterogeneous deployment of CCAs, it does put the fairness of the internet at stake. And so in this work, we ask, can we actually measure what CCAs are deployed in the internet today? Because anyone can deploy whatever congestion control algorithm they want. So let's more precisely define the problem. If I have some sender and I'm the receiver, how can I figure out what CCA the sender is using just by looking at the traffic sent between the third-party sender or server to me, the receiver? So most of the prior works addressing this problem have tried to classify CCAs by estimating the congestion window, or the C-wind for short. So the C-wind is an internal state variable for TCP and cannot be directly measured. So these techniques seek to estimate this through active measurement. And so the two prior works I talk about in this paper is Inspector Gadget and Gordon, which were both published in 2020. So the first limitation of this work is that it typically seeks to force packet losses and timeouts, and ultimately then is assuming that the CCA is going to react to those losses. And so it needs special tests for CCAs that are not loss-based, like BBR. In addition, this work does not support all of the built-in CCAs in Linux. In addition, this work, particularly Gordon, is inefficient and intrusive. In order to collect these C-wind traces, they need to try and do methods like forcing timeouts, among other behavior, which in some cases has them acting as a misbehaving receiver. So this leads both to high measurement overhead, requiring a lot of time to collect traces and a lot of data to be transferred between the sender and the receiver. Lastly, Inspector Gadget is what we call closed set. So this means that we're assuming that a server will use a CCA in the training set. So they're unable to say that a CCA is not in the training set and is unknown. Given these limitations of prior work, our goal is to design a new CCA classifier with higher coverage of known CCAs, better efficiency, and that is open set, meaning able to discover new CCAs without considerable effort. So our key insight in this work is to achieve this goal that rather than trying to estimate the C-wind with these active measurement techniques, we can actually observe CCAs passively in their natural habitat at the bottleneck queue. And so in order to collect queue occupancy traces, we build a test bed using BESS, a software switch, so that we can force a local bottleneck. And so BESS allows us to change the link rate to make us the bottleneck by setting it small. We can also control the RTT by delaying ACKs, and we can control the queue size, as well as record every time a packet enters, leaves, and is dropped by the queue. So we can issue HTTP requests from a web server and classify what CCA that server is using. While there is prior work that forces a local bottleneck, we are the first to record queue occupancy traces and use that for classification. So we call this technique nearly passive because we're not forcing packet losses or any other particular behavior. We're just forcing us to be the local bottleneck. So here I'm going to show you some traces we collected from our data, our testbed. So each CCA has a distinct Q occupancy time series. So here I'm showing you an example of BBR, cubic, and big. And we even see that we can get unique Q occupancy traces for CCAs that are very similar, like variants of Reno, including Westwood and Yap. So because we have these Q occupancy traces, we can naturally frame this question as a time series classification problem. So I have my labeled Q occupancy traces as my training data to my classifier. And when I want to classify a new trace, we input some unlabeled testing sample, and our classifier will either say that it's in the training set and it's a predicted label, or that we believe it's not in the training set and it is unknown. There are many time series classification methods, but the most classic method, which has been shown to be effective for a wide variety of problems, is one nearest neighbor plus something called dynamic time warping. So many of you probably know how one nearest neighbor works, but for a refresher, one nearest neighbor takes a set of training samples and computes the distance between a testing sample and all training samples. And then a testing sample is given the same label as the closest training sample. But in order to use one nearest neighbor, we need to be able to compute the distance between the two time series. So let's talk about how we can do this. So let's consider a specific example here where we have a time series of TCP cubic. And let's say we want to compare it to another trace that is nearly identical. Notice here the different phrases of the algorithm are nearly identical. The simplest metric for computing the distance between the samples is using Euclidean distance. So this is a one-to-one mapping between the points in the two time series. I take the distance between the first 2 points and add that to the distance of the second 2 points, and so on until I have the distance between all points. So this leads to a small Euclidean distance here because the traces are nearly identical. Now let's consider a second time series here where it's still cubic, but the phases don't exactly match here. They're misaligned. So in real traces, this shift can happen because we're doing this measurement over the internet. So there may be unexpected packet losses, slightly changes in delay, and other unpredictable changes that could result in traces not exactly being matched up and exactly the same. But unfortunately, Euclidean distance is not robust to shifts in the time series because it is still a one-to-one mapping. And so the distance here is larger, even though it's still the same CCA. In contrast, to handle these shifts and stretches, dynamic time warping allows a one-to-many mapping where any point can map to any other point with the limitation the lines can never cross. So DTW can account for shifts and stretches, and it does not have the same issues of Euclidean distance because it is a many-to-one mapping, unlike the one-to-one mapping of Euclidean distance. And so we use DTW as our distance measure. So I briefly am going to describe how CCAnalyzer works end-to-end, but I don't have time to go into any detail, so please read our paper. So first, we collect 20-second Q occupancy traces for 4 network settings for a particular website we want to classify. Next, we compute the distances for each of these samples to the closest training sample for those same settings. And so now we have the closest label and the distance to that label for each of these 4 samples. Next, we apply a distance threshold. That is, if the distance to the closest label is greater than some threshold T, it's going to be marked as unknown rather than get the label of the closest training sample. And then finally, we're going to vote across those 4 settings and give the website a final label. So to evaluate a CCAnalyzer, we classify each CCA 5 times with training samples collected from an AWS web server and testing samples from an Azure web server. And we see that CCAnalyzer is perfectly accurate for all 15 CCAs, because in part because of our voting method. We're more accurate than Inspector Gadget, which is likely less accurate due to overfitting for its machine learning classifier. We also compare it to Gordon. And so while Gordon is nearly 100% accurate on the CCAs it supports, it does not support all 15 CCAs in place. And so CCAnalyzer has higher coverage. In addition, we also want a CCAnalyzer to be more efficient. So here we compare the amount of bytes that need to be transferred from the third-party server to the client to collect traces for CCAnalyzer versus Gordon. And we find that on average, CCAnalyzer can classify with 85% fewer bytes transferred between the server and the receiver. In addition, we compared the amount of time it takes to collect those traces, and CCAnalyzer is 40 times faster. So a really interesting and killer part of the solution is these DTW distances, which actually reflects how similar these CCAs are. For example, here on the left, I'm showing you a BBR testing sample and its closest training sample, which is also BBR. And on the right, I'm showing the distance for this BBR testing sample to all of the training samples. And we can see that it's closest to the other BBR samples and similar CCAs like Vegas and New Vegas, while it's far away from Reno and cubic variants. So we can actually use this distance measure then to compare the testing samples to one another. And so we can cluster the testing samples based on this district method, which is pretty cool. So we use hierarchical clustering. So each trace starts in its own cluster, and then we compute the distances between each pair and cluster what's closest together. So this dendrogram illustrates what these clusters would look like given the distance between the traces. So I want to zoom in here and talk about how we're actually able to use this clustering to validate our results and fix traces that were likely incorrectly classified. In particular, I'm going to show you an example here where we end up, if we use the same distance threshold that we use to mark stuff as unknown, it would end up putting the different traces here that are in boxes into the same cluster. And so I want to draw your attention to the cubic n equals 151 cluster. So there's 151 samples here that are all going to be labeled as cubic because 20% of the traces in that cluster are cubic, while the others are marked as unknown. So next we use CCAnalyzer to classify the top 10K websites from Chrome's UserX report top list. I don't want to focus too much on the individual numbers here. I just want to call out a couple important points. We do break down our results in the paper by CDN. In particular, out of the 10K websites, we found most of them were using the CDN Cloudflare. In addition, we found a large fraction of those were using BBR v1. And we see this pattern with other large CDNs where a large fraction of them are using BBR v1. While we see Fastly also using cubic. Lastly, I also want to call your attention to the fact that we expected Google to be using BBR v1 when we did this measurement, but we found that most of the traces we collected from Google were marked as unknown. And it turns out we were able to discover unknowns without doing any additional tests. In particular, when we clustered all our Google samples together, we realized they were all using the same CCA, which turns out to be BBR v3. Here on the slide, I'm showing you scholar.google.com trace compared to its closest trace from our training set, which is BBR, but you can see it is different. The really neat thing about this is we can discover new CCAs and we don't have to do any additional tests. We can just cluster with our distance metric. And so the main takeaways from this talk, there are three. CCAnalyzer collects QXP traces and uses a time series classification approach to classify CCAs. CCAnalyzer is open set and outperforms prior work both in efficiency and accuracy. And we find widespread deployment of BBR v1 at large CDNs, and we're able to discover BBR v3 without having any samples in our training set. Thank you.